This is video 1 of our Chapter 6 and 7 AP exam review. I'll go through Chapter 6 in this video. So let's take a look at some of these multiple choice questions. I'll let you figure out the first 4, and let's take a look at the 5th one. Now, Chapter 6 was over the electronic structure and electron configuration. So this one, number 5, asks about electron configuration, the business about 1s2, 2s2, 2p6, and so forth. So here it says we want the manganese plus 3 ion. Now, if you take a look at the periodic table, manganese, here's a quick little diagram. Manganese sits right in the middle, in actually the 5th column of the D block. So it's the 5th element in the D block. And right before it then is argon. So if you were to draw the noble gas configuration for manganese, you would get yourself argon, and then this is 4, so 4s2. Remember that the D is 1 less, 3D. Now it'll be 5 if it were the regular argon. Now, manganese. Now, because we have a plus 3 ion, this means we lost 3 electrons. Now, the rule for losing electrons is you lose them from the highest occupied sublevel. So you first lose the 4 before you lose the 3. So these two are lost first. We need to lose 3 total. And then this is lost, and we end up with 3d1. Now this one represents the whole configuration. So argon, remember, is 1s2, 2s2, 2p6, 3s2, 3p6. So all the way out to here, and then 3d4. So this is actually the answer. Notice we don't have an S in here because those were lost from argon. We don't have one of the D's. Those were lost. So the incorrect way of doing it would be losing 3 D's before the S. This is the wrong way of doing it. You would lose the S before you lose the D. And that's kind of the idea. Good. So we'll also look at number 7 and 8. These are going to be the, let's see, unpaired electrons. So we're going to do orbital diagrams. If you recall, orbital diagrams had orbitals with electrons in them and so forth. So let's take a look. Here it says number 7, the atom that contains exactly 2 unpaired electrons. So if we take a look, for example, at sulfur, if we find sulfur and try to get its configuration, sulfur's configuration, this is kind of a review. We'll do noble gas. Will be neon as the previous noble gas, after which we have 3s2 and 3p4. Sulfur is the 4th element in the p block. So each s sublevel had 1 orbital, each p had 3 orbitals. That was 3 orbitals. Remember, each d, if we were to have a d that has 5 orbitals, and usually you don't go beyond the d. So if you take a look then, since we have 3 orbitals in the s, and then the p, 1 in the s, so we have 2 electrons, up, down. Now remember, the way electrons get filled is you first fill the up electrons and then the down electrons. So the correct way of doing this would be up, 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 and then down to get us the 4 electrons. This gives us 2 unpaired electrons, which is what we're looking for. So sulfur then is the answer right here. 8 says the atom that contains only 1 electron in the highest occupied energy sublevel. Now remember that the 3 is the energy level, the S and the P are the sublevels. These are sublevels. So we're looking for the element that only has 1 electron in the sublevel. If you take a look at the periodic table again, this is a very convenient way of drawing the periodic table, you'll find that gallium is sitting as the 1st element in the P block. So gallium is actually the answer because it's the 1st element in the P block, so its configuration will be P, only 1 element, or 1 electron. If you take a look at something like bromine, bromine is the 5th element, right next to the noble gas. So bromine will actually have 5 electrons. So if you have 5 electrons, you have 1 unoccupied electron. But we're looking for only 1 in the highest occupied sublevel. So sublevels, remember, are blocks. So the D sublevel represented by the D block, S sublevel by the S block. It's rare that they ask anything about the F block. So usually you don't have to think about the F block, but you do want to think about the others. So this is electron configuration. Let's take a look at a question on the back that deals with some energy, light energy, because the way we found out about electron configuration is by looking at light energy. So take a look at number 11. This one will actually connect some graphs and some observational, experimentational evidence. So 11 says, a sample containing atoms of carbon and fluorine was analyzed using X-ray photoelectron spectroscopy. This just means we're going to fire X-rays at them and see how the electrons are released. The portion of the spectrum showing the 1s peak for atoms of the two elements shown on the right. Now what they're saying, so we have ourselves fluorine and carbon, so let's visualize fluorine and carbon. Fluorine is the fifth element, right before the noble gases. Carbon then is the second element here. So we know that as we go this way, this actually gets a little bit into chapter 7. We know that as we go this way, the size decreases. Elements get smaller and smaller and smaller. So we know fluorine is has a smaller radius than carbon, so it should be tougher to remove fluorine's electrons. So let's take a look at what it says. So it says which of the following correctly identifies the 1s peak for the fluorine atom and provides an appropriate explanation. Really quick, the graph, as you see, this is binding energy, so this is essentially how much energy the electrons have. And notice it increases this way. This is important to see. And intensity is just how powerful that signal is, essentially. So the question is, which peak, the second or the first peak, corresponds to fluorine? Now, because fluorine is further along, which means you have more electrons and more protons, the reason why this size decreases is because your effective nuclear charge increases, pulling the electrons closer to the nucleus. So fluorine should have a higher first ionization energy, should be tougher to remove fluorine's electron. So actually, peak X should be for fluorine, because notice this energy right here is 67, 68, versus this energy is about 27, 28. So this is definitely fluorine. So these two are out, peak-wise out. Now the question is it because it has a smaller first ionization energy, or is it because it has a greater nuclear charge? And it turns out that the nuclear charge is the better explanation. It's true that it has it actually has a higher first ionization energy. This is wrong. Sometimes they'll throw an answer in that matches, but it's not the best. So in this case, it says correctly identified. So B is the answer. We'll take a look at this idea in just a second in chapter 7 as well. Let's take a look at the second graph here. Very similar idea, but it actually uses the spectrum. So we have ourselves UV, infrared, microwave, radio. More energy this way. Ultraviolet rays have much more energy. So it says the diagram above represents the absorption spectrum of a pure molecular substance. So we have some sort of molecule, maybe C2H6, something like that. We don't know. Which of the following correctly indicates the type of transition observed for the substance in each region of the absorbed spectrum? So we have three possibilities: molecular vibration, rotation, electronic transition. The first question is, which of these will require the highest energy? Now, electron transition, that means we're removing electrons or moving electrons up from the nucleus. Which will have the highest energy requirement? Electron transition, most energy. Now, most energy corresponds to UV light, so electronic transition should be under region X right here. So these two are out. We got electronic transition. The next two possibilities are which one requires more energy, molecular rotation or molecular vibration? Now, rotation is if you have the molecule and you're just spinning it, which is easier to do versus if you have to constantly vibrate the molecule back and forth. Vibration turns out to have or to require more energy. So molecular vibration will be in the infrared, and the rotation will be in the microwave. So D is the best answer. I'm just kind of giving you these facts. Think through them. Maybe, this is more of a memorization idea, but it does connect to energies of molecular motion. Let's do a little calculation on the back. And then this allows us to use the equations which are given to you at the very first, or on the first page of the AP exam. So here we have a problem. Initiating most reactions involving chlorine involves breaking the chlorine-chlorine bond, which has a bond energy of 242 kilojoules per mole. Calculate the amount of energy in joules needed to break a single Cl-Cl bond. So this is how many kilojoules it takes if you want to break a mole of bonds. So we have 242 kilojoules over 1 mole. Anytime you have dimensional analysis with 2 units, just put them one above the other, just like so. It says it in joules, so let's first convert into joules. Now, a kilojoule, so kilojoules will go downstairs, joules upstairs. Just like kilograms and grams, a kilojoule is 1,000 joules. Now, what we'll do is they want a single bond. So we don't want this to be per mole, we want it to be per atom. Do we know how many atoms in a mole? Of course we do. It's 6.02 times 10 to the 23rd. We celebrate Mole Day on the 23rd of October. Festivities begin at 6 a.m. in the morning. And so this is 1 mole of anything. So 1 mole equals 6.02 times 10 to the 23rd. If you do this quick little conversion, you should get yourself 4.02 times 10 to the negative 19 joules, which corresponds to one little tiny bond, which has a tiny, tiny amount of energy, which makes sense. B says, calculate the longest wavelength of light in meters that can supply the energy per photon necessary to break the bond. There are 2 equations that are involved here, and these both are given to you. These are the ones I was referring to. It's energy equals hv, where v is the frequency, h is the Planck's constant. If you recall, we did some of these calculations. The second is c equals lambda v. Lambda is wavelength. So this is actually what they want. They want us to eventually solve for wavelength. So we'll use the first equation. We've got the energy. This is actually energy right here. So let's first solve for v, and then that'll connect us to the second equation, and we can solve for lambda. So the first equation rearranged to v, or frequency. This is actually not v. This is nu. This is the Greek letter n. That's how they write their n. So we have ourselves E equals, or E over h. So E is 4.02, 10 to the negative 19th. And then h is a Planck's constant. If you look this up, you'll find that it's this value right here, with appropriate units to match. And so if you divide the two, you get yourself 6.07 E14. Now, frequency is measured in inverse seconds or hertz. So you can put per second, or you can do inverse seconds, or you could have done hertz. Either one of those units would work. You always want to show units with your calculation, obviously. And then finally, let's calculate C, or use C to calculate wavelength. So we got ourselves wavelength. If we rearrange the equation now, right here, is C over nu. So we have 3.0 times 10 to the 8 meters per second. That's the speed of light. Our frequency from up here is 6.07, 10 to the 14th. And we get ourselves, if we divide this, we should get ourselves a value of 4.94 times 10 to the negative 7 meters. Now wavelength, here it says in meters, and because you have meters per second here, and you have inverse seconds here, the seconds would cancel out, you're left with meters, and that's how we have the meters. This turns out to be 494 nanometers, so they may ask you to convert from meters to nanometers, and if we know that a meter is 1 billion nanometers, you'll end up with this value. And this corresponds to the blue region of the electromagnetic spectrum, to the purple region, if you look it up. So that hopefully does light and electronic structure review. We'll take a look at the periodic table in the next video.